Hello everyone, and welcome to this course on computer network. So we are in the second class on this topic of internet routing. So in the last class, we have looked into the basic philosophy behind the internet routing, and you have learned about one specific inter-domain routing protocol, that is the distance vector routing protocol. So today we'll look into another intra-domain routing protocol, that is the link state routing protocol in details. And followed to that, we'll move towards inter-domain routing protocol or the border gateway protocol. So that is the basic agenda of today's class. So to start with, we'll look into the limitations of the distance vector routing protocol or the routing information protocol. So RIP is the actual protocol which defines the packet format, the messaging format, the message exchange protocols in distance vector routing. So as I was mentioning that we have two broad classes of routing protocol, the distance vector routing and the link state routing. So RIP is an example of distance vector routing, whereas OSPF or open shortest path first is an example of link state routing. So in the last class, we have looked into the distance vector routing protocol in details. So if you are interested into look into the messaging format, the messaging protocols in a distance vector, in a typical distance vector routing setup, you should look into this RIP or the routing information protocol in details. So the broad idea of the distance vector routing is that it uses a distributed version of the Bellman-Ford algorithm, where every node or every router they periodically broadcast its own distance vector, that is the routing table along with the cost metric. Now, whenever the neighboring routers they get that distance vector information, that means the routing table along with the cost metric, they update their own routing path by following a decentralized version or distributed version of Bellman-Ford algorithm. Now, what we have seen in distance vector routing, that one of the major problems is this count to infinity problem. Although there are many solutions which have been proposed to eliminate this count to infinity problem, but this kind of problem still exists in a network. There are no absolute solution which can remove this count to infinity problem completely, and that is why what we typically do, that we limit the network path. That the network cannot be beyond having beyond this many number of paths. So typically that setup is 15 in routing information protocol. So that means that whenever a particular router is updating its path cost information, whenever it will go beyond 15, it will assume it as an infinite, and it will assume that, well, from this node to that node, there is no path exist. So that way, we basically eliminate the count to infinity problem in a typical distance vector routing setup. So that is actually a limitation, because you cannot have a say network which having more than 15 hops. So on that kind of architecture, you will your routing information protocol or the distance vector routing protocol will not run. So that is the reason typically in an autonomous system, if you are going to use this distance vector routing class of protocols or the RIP protocol, we keep the maximum number of hops setting as 15. So that is the typical setup. So this is one limitation of the distance vector routing protocol. The second limitation is the high signaling overhead. That periodically you need to broadcast this distance vector table among the neighboring routers. So this distance vector table, whenever you are broadcasting it among the neighboring routers, it can result in increased utilization of the network resources, because that broadcast also taking up some amount of bandwidth from your network. And the third problem is that this algorithm is relatively slow to converge. To get convergence, you need information from all the nodes or all the routers in an autonomous system. Once you get the information from all the routers in an autonomous system, then you can say that, well, it has converged. But again, whenever you are getting information from a router, it is updating itself. So even if it may not converge. So that is why the convergence is very slow in a typical distance vector routing setup. So for these reasons, we have another type of inter-domain routing protocol, which is the link state routing protocol. So now we'll look into this link state routing protocol in details. Typically before 1979, the default ARPANET protocol was this routing information protocol, which is a distance vector routing protocol. Now, starting from 1979, the ARPANET routing protocol, it was replaced by link state routing protocol. Because this down to infinity problem, the convergence became slow, and they thought of to have another class of routing protocol over the internet, which is the link state routing. So the basic RIP protocol was replaced by this open shortest path first, or OSPF protocol. So OSPF is a link state routing protocol. So just like in case of distance vector routing, we exchange the distance vector information among the nodes. In case of link state routing, we exchange the link state information among the nodes. Now, why we are moving from this distance vector routing protocol to the link state routing protocol? The basic philosophy is something like this, that in case of distance vector routing protocol, you are first doing a routing path computation, and then you are exchanging that computed information with your neighbor. So you are finding out that to a particular sink or a particular destination, what is going to be your shortest path. Now, your estimated shortest path, that information you are sharing with others, and then your neighbors are updating their information based on that estimated shortest path information. So that is typically the reason why this distance vector routing protocol is slow, and this convergence is a problem in case of distance vector routing protocol. So that is why from the distance vector routing protocol, we move towards this link state routing protocol, as I was mentioning earlier. That this distance vector routing protocol doesn't work in an autonomous system which has number of routers more than 15. So that is why we move towards this link state routing protocol. Now, in case of link state routing protocol, the basic idea that I was mentioning, like you do not share this partially computed information, what we are doing in case of distance vector routing. So rather than sharing the partially computed information, what you do, you share the link state information. So from there, this link state routing name came. So what is the link state information? So the protocol is, as I was mentioning, it is very simple. So in the protocol, so every router, it discovers the neighbors and learn their network addresses. So every node periodically broadcasts its own information. Once that information is propagated in the neighborhood, then every node get that information, and from there it compute who are my neighbors, and we set the distance or cost metric to each of the neighbors. Now we construct a packet telling all that it has learned. So the idea is that I have learned about my neighbors. Now I will broadcast that neighbor information to other nodes. Now the difference here from the distance vector routing is that in distance vector routing, we are doing a partial computation of the shortest path, and that partial computation of the shortest path information we are exchanging with neighbors. Now here we are not computing that shortest path, rather we are just sharing the raw information with the neighbor. So I am just sharing the information that, hey, I have ABC as my neighbor, and my cost to A is 2 units, my cost to B is 3 units, and my cost to C is 4 units. That much of information is broadcasted in the neighborhood. So we are not computing anything, or we are not broadcasting any partially computed information across the neighborhood. Now this information, we call it as the link state information. So we are sharing the state of every links that every outgoing link from a particular router to my neighbor. So that information we are sharing. So we call it as the link state information. Now once every node receives that link state information from other nodes, based on that link state information, it can compute the network graph. We will see an example about how this network graph is being computed. Now, once every node has that entire network graph, then from that network graph, you compute the shortest path. Now, here you see that what is the difference from the distance vector idea. In case of distance vector idea, it was a decentralized or distributed Bellman-Ford algorithm. You partially compute your shortest path to everything, and then you broadcast that partially computed information. Here in case of link state routing, we are not computing anything, rather the raw information we are sharing with others, and based on that raw information, locally every node computes that network graph. And once you have computed that network graph, from that computed network graph information, you run the centralized algorithm to find out the shortest path. So that is the basic difference between the distance vector routing protocol and the link state routing. So we are going to see it with an example. So here is the first step about the link state routing. So the first step of link state routing is that you need to learn about the routers. Now to learn about the routers, when a router is booted, it first learn about the neighbors. So it broadcasts one special packet on each point-to-point outgoing link. Note that it used the broadcast IP address to broadcast that information. So that is one usage of the broadcast IP address to broadcast my link state information to others. So we call this packet as the hello packet or hello message. Through this hello message, I am informing others that hello, I am there to connect with you. So I am one of your neighbors. So once a router receives a hello message, it sends back its identity to that particular node. So here is the idea, like, so with say node R1, I have, say here is the node R1, and it is connected with three other nodes, H1, H2, and H3. Now remember that this routing protocol is getting executed on top of layer 3. That means on IP layer. Now the intermediate switches which are there, they do not take care of, or they do not become part of this route protocol, because they do not understand any layer 3 messages of the IP layer messages. So my end host, which is running the IP layer, and the intermediate routers, they become part of it. Now each router, it is broadcasting its information to all its interfaces. So router 1 has 2 outgoing interfaces, ETH1 and ETH2. So it will broadcast its hello message through this ETH2 and the ETH1 information, ETH1 interface. And the nodes which are connected at layer 3 over that interface, they will get that information. So R2 over its ETH1 link, it will get that information. H1, H2, H3, they are the end host, they are single interface nodes, so they will get that information through ETH2. Now from this sharing of information, I can construct a network graph like this one. So R1 has 2 interfaces, R1 ETH2 and R1 ETH1. These 2 are the interfaces of the same router, so they are connected. Now with R1 ETH2, I have 3 hosts which are connected, H1, H2, and H3. Similarly, over R1 ETH1, I have another interface of another router connected, which is R2 ETH1. So R2 ETH1 gets connected with R1 ETH2. So that way you can see that we can construct a network graph of the layer 3 interfaces which are there, to which you can broadcast layer 3 hello messages of the hello messages corresponds to the link state routing. So that way every router understands that what are the other nodes which are connected to it over different interfaces it has, and from there it construct a network graph. So that is the first step to construct this kind of network graph. Now, once this network graph is constructed, the second task is to set the link cost. Now, every link, it is assigned with a link cost or distance. So that can be hop count, that can be delay, that can be any other parameter like throughput that is used as the routing metric to find out the shortest path. Now, a standard approach in link state routing is that you use the inverse of the link bandwidth. So that means the higher capacity parts are the better choices. This minimize the routing cost. So whenever you are taking the inverse of the link bandwidth and you are computing a shortest path by minimizing the cost, so that means you are maximizing the bandwidth, you are taking the higher capacity part. So that is a standard approach. But many link state routing protocol, they also take hop count as a metric. So how many hops you are from one node to another. And some networks, it use link delay. This link delay is computed through the ICMP protocol. So earlier I mentioned about this ICMP protocol to you, Internet Control Messaging Protocol, which periodically broadcast or which broadcast different type of control messages over the internet to get information about neighborhoods or passing certain information from one node to another. So here is another example of the ICMP messages. So using this ICMP echo packet, you can compute the link delay between two layer 3 or two IP layer nodes. So once you are sending ICMP echo request to one node, it will send back an ICMP echo reply. Now, from your time, whenever you have sent this ICMP request to the time whenever you have received back the ICMP echo reply, by subtracting these two, you will get the round trip time. So now half of the round trip time you can assume as the one-way latency. So that way, using ICMP echo request and echo reply, you can find out what is your link delay. So this link delay can also be used as a metric for computing the routing. Now, if you are reducing the link delay, that means you are reducing the end-to-end delay in the network. So that way, you can set up the link cost in a link state routing protocol. Now, once you are set up this link state routing packet, then the next task is to set up or build this link state packet and broadcast it. So how this link state packet are being set up? So every node, it finds out that what is the cost to its neighbors. So say node A, it has B and E as the neighbors. So it finds out that A to B, the cost is 4, A to E, the cost is 5. So A to B, the cost is 4, A to E, the cost is 5. Yeah, so A to B, the cost is 4, A to B, the cost is 5. And along with that, it introduced two other parameters called the sequence and age. So this sequence basically denotes that the link state packets which are being broadcasted at every round, so that you can reduce the stale packets or the old packets from consideration. Say, for example, you got a packet with sequence number 10, another packet with sequence number 12, we will going to consider the packet with sequence number 12. And the age basically denote that how much time that packet will rebroadcast in the network. So the way it happens is that A first compute its link state packets with the link state information that it has a path to B with cost 4, and it has a link to node E with cost 5, then A will broadcast that information. So B and E will receive that information. When B and E is receiving that information, they are also going to broadcast that information to their outgoing links. So that way, this particular link state packet will reach to all the nodes in the network. So similarly, every other node, they will construct the link state packet corresponds to them. So say for node B, the link state information is with A, it has a part of 4, cost 4. With C, it has a part with cost 2. With F, it has a part with cost 6. Similarly, C constructs with B cost 2, D cost 3, E cost 1. D construct as the C cost 3, F cost 7. So that way, every node basically construct the link state path information. Now, once they are constructing that link state path information and it is broadcasting that link state path information to all of its outgoing interfaces. So the broad idea is something as I was mentioning earlier, that A will broadcast to its interfaces, like A will broadcast to B and E. Now, once B is getting that information from A, B will broadcast it to C and F. Once C is getting that information, C will broadcast it to E, F, and D. So that way, every individual link state packet generated from all the nodes, they will get broadcasted from all other nodes in the network. So every node will get all the link state packets. So for example, if you take a random node like node F will get the link state packet from A, from B, from C, from D, and from E. So for all the link state packet, it will get that information. Now, as I was mentioning, that you need to distribute that link state packet. So all of the routers must get all of the link state packets quickly and efficiently. Now, if different routers have different information, the routing inconsistency may occur. So that is why we share the same link state information to all the routers in the network. In link state routing, it uses flooding to distribute the link state packets to all other routers. That means that each link state packet contains, as I was mentioning, that each link state packet contains a sequence number that is incremented for each packet sent. So it is used to identify the stale information. So here you can see an example of a typical link state packet. So the right hand side diagram shows a typical link state packet, and the left hand side shows the packet corresponds to the OSPF protocol. So here you can see that it sends that link state age, the packet type, the state ID, the advertising router, the router which is advertising the information, the sequence number of the packet, the checksum, and the length of that link state information. So then it contains the set of link state information. In case of OSPF, you will see that it has the pretty same information: version, type, packet length, the router ID which is broadcasting the things, the area ID, the subnet from where it is being broadcasted, or the autonomous system number within which it is getting broadcasted, the checksum, and it also uses authentication information. So this authentication information is used to exchange authenticated OSPF packet across the routers, so that you cannot send any kind of unauthenticated information, or you cannot raise any kind of attack with the help of this OSPF link state broadcast information. And finally, there is this data field. So this data field basically contains the link state information. That with A, you have a path to B with cost 4, not path, a link to B with cost 4, a link to C with cost 6, a link to X with cost 9. That is the link state information which is being broadcast. So here I'm giving you an information. Say here is a typical router. Say we are taking node E for consideration. Now from node E, it broadcasts the link state information to its neighbors. Say here is the link state information from E. Say for simplicity, we are considering the hop count as the cost. So E to D, you have a link with cost 1. E to B, you have a cost link 1. E to C, you have a cost link 1. Now, you construct a link state packet and broadcast that link state packet to all the outgoing links. Now, that way, D, B, and C will get that information. Now, once D, B, C get that information, they will further rebroadcast it. And that way, that information will get propagated in the network, and everyone will be able to construct the network graph out of it. So, it is something like that. If A finds out that, well, from E, there is a link to B with cost 1. From E, there is a link to D with cost 1. And from E, there is another link to C with cost 1. Then you can actually combine this information together and find out that, well, from E, you have to create a edge to B with cost 1, to C, another edge with cost 1, to D, the third edge with cost 1. So that way you can construct the entire graph. So once a link state packet is received, the sequence number is incremented. If the sequence number is higher than the last observed link state packet, then it is accepted, otherwise it is discarded, as I was mentioning. Now, one problem that you might think of, that what if the sequence number wraps around? Now, typically in OSPF, we use a 32-bit sequence number. Typically, we send one link state packet per second. If you consider that, it will take around 137 years to wrap around. So, this question of wraparound doesn't come in case of link state routing with OSPF. Now, every entry in the router is associated with an edge. It denotes the lifetime of an entry, as I was mentioning. It deletes the old entries from the routing table. So once that edge is getting passed, it deletes that edge. So that's why you need to periodically broadcast this link state packet to ensure that the network is live. That also ensures that, well, if some router gets shut down, or if there is a failure in one router, that information quickly propagates to its neighbor, because it will not get any kind of link state packet. And after this edge is over, it will delete the old entries from its neighborhood, and that information about the failed router will get erased from the link state table. Now, once you have that link state information, every node will get that link state packet. Here is an example. So every node will get the link state packet from all other nodes in the autonomous system. Now, once you are getting the link state packets from all other routers in the autonomous system, so remember that I am using this two terminology, node and router, interchangeably in this talk. that typically we do. Sometimes we call it as node, sometimes we call it as router. Now, once you are getting that information, so after you get that information, then you can construct the entire network graph. Well, so whenever you are getting, so for example, you think about node C, it has received this link state information. So from that link state informations, let me take the pen. So it is, say, consider node C. So node C has got this link state packet. So once node C will get that link state packet, you can reconstruct the links. So from the link state packets, you can see that, well, from A to B or B to A, there is a link with cost 1. From B to E and E to B, there is a link with cost 1. From B to C and C to B, another link with cost 1. From E to D, D to E, link with cost 1. E to C, C to E, link with cost 1. E to D, D to A, link with cost 1. Now here you will see that both the bidirectional links are having same weight because we are taking hop count. But if you take other metric like inverse of the bandwidth, delay, the cost may change. Then in that case, you might have to create two different links. So that will become a directed graph. So from B to C, I will have one cost. From C to B, I might have another cost. But if you are taking hop count, it is symmetric. So from A to B and B to A, you will have the same cost. That is so. So that way, once you have that link information, then obviously you can construct a graph. You can construct the graph with 5 nodes, A, B, C, D, and E. Then A to B, you will put an edge with cost 1. From B to E, you will put another edge with cost 1. From B to C, an edge with cost 1. So that way you can create the entire network graph. Now, once you create that entire network graph, now everything is in your hand. You can run the Dijkstra's algorithm or you can run the Bellman-Ford algorithm. And now you see you don't need to run the distributed version of the Bellman-Ford algorithm, what we have done in case of distance vector routing protocol. So in case of distance vector routing, every node partially computed the information, and that partially computed information have been broadcast. So that was a kind of distributed version of the Bellman-Ford algorithm. But here, rather than doing that partial computation, you are sharing that complete information, and that complete information sharing, you are constructing the network graph, and then you can run a centralized version of that Bellman-Ford algorithm or the Dijkstra's algorithm independently or on every node. So every router can independently run the Bellman-Ford algorithm on that constructed graph or the Dijkstra's algorithm, whichever is being set up by the network administrator. And then it can find out the shortest path between all the source destination and accordingly build up the routing. Now, in case of link state routing, or whenever we are talking about this OSPF protocol, this link state messages are the overhead for the link state routing. So you have different type of link state routing messages. Here is an example for OSPF. So you have the hello messages to use the neighborhood establishment. You have database descriptor message or DBD or DD message. It broadcasts a local routing database among neighbors to check the consistency of the database information among the routers. Then the link state request message, LSR message, explicitly request the link state information based on the database comparison. If database there is mismatch in the database, it will again get the link state information. Then the link state update information to forward the link state information. Then the acknowledgement messages to acknowledge the receipt of a link state. So you have a set of messages which need to be continuously exchanged among the neighbors. So that way it also introduces a good amount of overhead. In summary, we have seen that in case of distance vector routing protocol, we have this overhead of convergence as well as this count to infinity, as well as the messaging overhead. In case of link state routing, convergence is a factor, but as long as you are getting the link state information from all the routers in an autonomous system, you will be able to directly convert, because now you are running a centralized version of the algorithm independently at every router, rather than running a distributed algorithm. But again, the overhead is these link state messages. You need to periodically broadcast that link state messages among the neighbors. So that also again limit the size of the autonomous system. If your autonomous system becomes very large, you will not be able to propagate that many number of messages. It will take a huge amount of bandwidth, and it will take a long for that link state information to get populated. So that is why also in case of OSPF, we limit the number of nodes or the number of routers that can be there within an autonomous system. So from that context, nowadays this OSPF or RIP, they becomes almost give almost similar performance. It is entirely on the administrator of an autonomous system to choose which variant of routing protocol it will use within the autonomous system. And that is actually an interesting factor. So it is not like that all the autonomous system in the globe they are using the same routing protocol or same inter-domain routing protocol. So different autonomous system may use different inter-domain routing protocols. So some autonomous system may use OSPF, whereas some other autonomous system may use RIP. So that means within an autonomous system, you have a disparity of algorithms, routing algorithms. So certain autonomous systems, they are using OSPF, and certain other autonomous system, they are using RIP. And the entire internet is like that. So all the autonomous system that you will see, different autonomous system, depending on how the network administrator has configured that particular protocol, they might use different version of the routing protocol. So some might use RIP, some might use OSPF. Again, if someone is using OSPF, it might happen that someone is using say hop count as the link cost, and some others are saying using say link delay as the link cost. So that's why the configuration of the OSPF can also vary across different autonomous systems. So that makes a kind of complicated architecture that within an autonomous system, it is entirely on the network administrator that which particular version of the protocol he or she will use and what configuration he or she will put. And with that complexity, we move towards the inter-domain routing protocol that whenever you are moving from one autonomous system to the next autonomous system, how will you select that which is going to be your next autonomous system? So we'll look into that in details. Okay. Now, with this intra-domain routing protocols, so we'll look into the inter-domain routing protocols in detail. So the idea of this inter-domain routing protocol is that now whenever you are moving from one autonomous system to another autonomous system, so typically you think about this autonomous system hierarchy, like the diagram that I have shown here. So the entire network is divided into multiple autonomous systems, and these autonomous systems are basically interconnected with this edge router or the gateway router or the border router, whatever you call it, which interconnects two different autonomous systems. Now, whenever you are sending a packet from a source to a destination, your source is residing in one autonomous system and the destination is in another autonomous system. Now, whenever you are going through an autonomous system, how the packet will be forwarded from within the autonomous system, that will be decided by your intra-domain routing protocol, that is by OSPF or RIP, whatever the autonomous system administrator has set up. But then, say your source is there in autonomous system 1. So here is your source, and your destination is there in, say, autonomous system 4. Now, if that is the case, then how you are going from AS1 to AS4, that becomes the question, that whether you are going to be via AS5 or whether you are going to be via AS2, AS3. So that is the question. So that resolution is being done through this inter-domain routing protocol, or sometimes we call it the exterior gateway protocol. Now, on this exterior gateway protocol, we'll look into the one typical exterior gateway protocol which nowadays used widely over the internet, and that is called the border gateway protocol, or BGP. We'll look into the BGP in details. But before going to BGP, let us look into some terminology. One is the multi-homed AS or multi-homed autonomous system. The multi-home autonomous systems are the autonomous system which has connection to more than one autonomous system. That means, say, autonomous system 1, it is connected to autonomous system 5 as well as autonomous system 2. Now, all these autonomous systems which are actually shown in this diagram are multi-home autonomous systems. So they are connected with more than one autonomous system. That basically means that you can take the data from one autonomous system and pass it to another autonomous system via that autonomous system. Okay, so that is called a multi-home autonomous system. Then there are the stub autonomous system. The stub autonomous systems are autonomous systems which are connected to only one autonomous system. So that means to get the internet connectivity, you need to always rely on your parent autonomous system with which you are connected. And then the transit OS. Transit OS is the type of multi-home autonomous system which allows transit traffic. So transit autonomous system means, say, one autonomous system, say A, I am considering another autonomous system B, and then the third autonomous system C. Now, if you want to transfer data from A to C, B works like a transit autonomous system, which is taking the data from A and forwarding it to C. So that means B is forwarding the data traffic, which doesn't belong to it, rather it belongs to other A's, and for those A's, it is using itself or its resource as the for that kind of transit traffic. So it is transiting through B and the A to C traffic. Now, as I was mentioning, that each AS can run its own inter-domain routing protocol. We call them as the interior gateway protocol or IGP. So we have multiple different type of IGPs. OSPF, which uses the link state routing philosophy, the routing information protocol or RIP. That is a kind of distance vector routing protocol. There are other different type of IGPs like ASS IGPs. There are the static routing, or it can be used a mix of different routing protocol. That means different subnets are using different routing protocol. That can also happen. So it can use the static routing. So routing tables are statically configured. It doesn't run any kind of routing algorithm. Now, this inter-domain routing problem is like the ASS, the autonomous systems, they share the reachability information. So what is reachability information? The reachability information basically says that, hey, autonomous system X is reachable via autonomous system Y. So that means if you want to forward a packet to autonomous system X, you give it to autonomous system Y. Autonomous system Y will in turn give it to autonomous system X. So that we call as the reachability information. So in case of inter-domain routing protocol, that every autonomous system, they share the reachability information among themselves. So it is basically a description of the set of IP addresses that can be reached via a given case. Now here you see that in case of interior gateway protocol or inter-domain routing protocol, we were concerning about every individual node in the network, that how I am going to reach to a particular node. Now here, whenever we are talking about the inter-domain routing protocol or the exterior gateway protocol, in that case, we are not concerning about every individual node, rather we are concerning about the entire subnet. So this is something like the hierarchy we use in case of our postal delivery. So you again think of that how our postal delivery are being made. Say you are posting a letter for your friend which is there in, say, IIT Delhi. Now, whenever you are posting it to the Kharagpur post office. Okay, now the Kharagpur post office, it will see that, okay, it needs to be passed to Delhi. It will not look into that whether it is in IIT Delhi or which hall in IIT Delhi. It will just see that it needs to be passed to Delhi, and to pass to Delhi, I need to send it to the Kolkata GPO. So Kolkata GPO is my next hop autonomous system in terms of my networking term. So you forward it to the Kolkata GPO. Now Kolkata GPO will see that, well, I need to forward it to Delhi. So it will forward it to Delhi. Delhi will see that, okay, this address belongs to this house khas area. So I have to post, or I have to send this letter to the house khas post office. Again, you see that the Delhi post office, it is not looking into that which hall within IIT Delhi it has to deliver that letter. That ground level information it is not looking into. It is just looking into in which area it needs to forward it. It needs to forward it to the house khas area, so you forward it to the house khas post office. So it will forward it to the house khas post office. Now the house khas post office, it is the last hop. So it will see that which particular hall in IIT Delhi it has to deliver the letter, and then it will deliver that letter to that hall in IIT Delhi. Now, what learning do we get from here? That at the further steps, you just take an abstraction of the locality, that in which locality you need to forward that message. Now, once it reaches to the concerned person of the final destination locality, then that concerned person will take about individuals who are residing in that locality. So the same philosophy we apply in the internet. So first, whenever you are forwarding a packet, say from your IIT Kharagpur to IIT Delhi, so from your machine, it will use some intra-domain routing protocol or some interior gateway protocol like OSPF or RIP, whatever has been configured for the IIT Kharagpur network. It will use that to pass it to the IIT Kharagpur gateway. Now, once it is reached at the IIT Kharagpur gateway, then it will not look into that individual device level details. It will only see that, well, in the Delhi region, I need to forward it. So it will find out that in which autonomous system I have to forward it. So there it will see that, okay, if I need to forward it to this particular subnet, I can forward it to this autonomous system, say the ARNet autonomous system, and the ARNet autonomous system will take care of to forward it to the IIT Delhi autonomous system. So it will just send that information to the ARNet autonomous system. So that way the packet will be being forwarded. So at the farthest level, you look into the abstraction of the locality, and then once the packet reaches at the locality, you look into individual node level. Now to construct this locality graph, this autonomous system share the reachability information. But here what is our challenge? That each autonomous system has to determine its own routing policy. And these routing policies can be complex. So here is a typical routing policy that is being applied, that whenever possible, I prefer to send traffic via ASX than via ASY, but I will use ASY if it is the only path, and I never want to carry traffic from ASX to ASY or vice versa. So see, it is a very complicated policy, and this kind of policy actually happens in case of a typical network. So the policy basically says that, okay, I am an autonomous system, say I am autonomous system A, I am connected with two other autonomous systems, X and Y. Okay, so A is a multi-homed autonomous system, A is connected with X and Y. Now what this routing policy says, that I will prefer to send traffic via ASX than via ASY. That means if X is available, I will prefer to transfer the traffic over X. But I will use ASY if it is the only path. That means if sometime if X is down, then I will use Y to send the traffic. But I will never want to carry traffic from ASX to ASY or vice versa. That means I don't want to be a transit autonomous system, although A is a multi-home autonomous system. So if the traffic originates at X, but it is destined to Y, I will not forward the traffic via myself. X will find out another path to send the data to Y. Or similarly, vice versa. From Y, if the traffic originates at Y, I will not take the load to send it to X. Y will find out another path to send it to X. So this is the kind of complexity in the routing policies that happen in the network because of the inherent contract between individual service providers. Say one service provider is Airtel, another is Vodafone, the third is say BSNL. Now whether Airtel will want to act as a transit traffic for BSNL or not, that depends on what is the contract between Airtel or BSNL. So there comes the kind of market policies or their business regulation, their business policies, all these things. So here you will see that whenever we are looking into the autonomous systems level and we are trying to forward the data, it is not about the technical thing, like it is not always about using a shortest path to forward the data, rather it is about the policies which might be driven by the economy, by the business, by the government. Government can set their own regulations that, well, I will not get traffic from this autonomous system because this autonomous system is to some country from where I don't want to get any traffic. So this kind of policies actually implies the rule. So you must have heard about this, the Great China Firewall, right? So China do not allow a lot of traffic within their network. So that is the kind of policies which is being set up by the China government, that it will not take any data from the autonomous systems which are there in US. Something like that. So this kind of policies actually drive this exterior gateway protocol or the border gateway protocol.